Okay, welcome to the third session here on Intro to Data Analysis with R. In this session, we're going to be looking at various fundamental data types. So I'm going to base this around chapters 14, 15, 16, and 20 of R for Data Science, and I've linked the chapters there on the Markdown sheet for you. So the idea of this session is to give you a useful basis in a lot of the fundamental basic data types in R, and this is going to be useful for exploratory data analysis, which we'll talk about in a later session, or some confirmatory analysis, hypothesis testing, survey analysis, natural language processing, machine learning, anything like that. It's useful to have a good grounding in the data types that you'll encounter in R. So I'm going to start the session looking at strings and various forms of string manipulation in R. Again, we'll need the tidyverse package. Let me just quickly load that into the environment, and now we can go with that here. So the idea of these strings is this is going to be useful for any kind of natural language processing, any sort of text analysis techniques that will come up in the coming weeks. I'm going to cover the basics of strings, but I'm going to move through that quite quickly, and I'm going to talk about some regular expressions, regexes, and we'll see how we can use those in our text analysis. The idea of regular expressions is they're useful because most strings, the most text we encounter, is often very unstructured or at least semi-structured. So it's difficult to work with, and we need to have a different language. So regular expressions are a sort of a sub-language almost, which we can use to describe patterns in text. So we'll be using the string R package for string manipulation, and luckily for us, it's part of the core tidyverse package, so we don't need to import anything else. So as you should be familiar, or hopefully you are familiar by now, strings, that's just any kind of text. You can create them within double quotes or within single quotes. Same thing, doesn't matter as long as you are consistent with what you've done. So I've got two strings here, string 1 and string 2. The idea of the double or the single is if I want to include a double or a single in it, then you can use the other type. If I wanted to include a literal double quote within a string that has double quotes, we need to escape it. And for that, as with many other programming languages, you use the slash character to indicate that you are escaping it. And obviously, if you want to have an actual slash, you need to have a double slash. So we'll encounter a few of these different escape characters throughout the session. There's a handful of other ones. So \n is for a new line. \t is for a tab character. We'll also see some strings like this, not so much in this session, but when you get to text manipulation, natural language processing, and text cleaning in a later session, you'll often encounter things like this. So this is, in this case here, U00B5. It's for writing non-English characters, but we can work with those when we get there with tidy text and tidy text models and things like that. So if I run this line of code, you'll see that is for that's the mu character if we want to represent that there. Okay, so base R contains many different functions for working with strings, but I'm going to try avoid them as much as possible because they're often quite inconsistent. So the idea of the string R package is it does the same things, but it's much more consistent in how you do it. And that's easy for us as programmers if everything works in the same way. They have intuitive names. They all start with str, and they all use a very similar pattern. So for instance, for length, we do str_length. And if I run that here, you give it the strings you want. So in this case, I'm giving it 3 strings. The first one is the string A. The second one is R for data science. And then the third one is NA. So we'll see. So it tells us that A is 1 long. 18 characters long is for the second string. And then the third string is NA. So the basic format of that is str_length. And as you can see here, by having them all start with str, and if I go underscore, this gives me all the different options of the functions in the package. So strc, conv, count, detect, and so on. And we can then see what the various functions are actually doing. So in this case, I want length, and I can just click tab, and then I have it there. And let's give this is my name, Doug. So this should tell us that this is, 4 characters long. Sorry about that. I just need to do Command Enter. So we can see there that is now 4 characters long. So with this figure there, this pulls up the tooltip, And if you're working in RStudio, this is very useful because now every string R function starts with str, and we can now scroll through this to see, is there a function to extract or look for duplicates or detect or whatever the case is. And then you can see here, it actually even gives us the structure of the function. So what does it expect if we want to use that function? So this common prefix is extremely useful for us. So let's look at a few more. If we want to combine strings, we can use strc. So in R, the C character stands for combine. So you've encountered here, I've got C and then I've got these three. So I'm combining A, R for data science, and NA into a single vector. So that's what it's working with there. Well, we have a string version of that. So if I run this, you'll see that we get a single string that we've combined them together like that. We can also pass a sep argument to it, and that'll put a comma in between them, whatever I tell it to separate them by. Okay, so that's some basic working there with string R, and obviously, as you saw here, there's a lot of different functions in the package that you can use, but they all follow the same general format, and that's the beauty of the tidyverse packages. But let's get into some string subsetting. That's one of the main things we actually want to even do with strings, is extract substrings from a string. So with string R, we can use str underscore sub to give us a substring. So we can give the start position and the end position. So in this case, I'm saying take x and give me the from the first to the third of x. So let's run that there, and it's going to give me the first three characters of apple, the first three characters of banana, and the first three characters of pear. So x is, in this case, a vector that contains three strings, but we could also instead just pass a single string to this. So this could be, let's again say, it's my full name, and we just want the first four characters. So if I run this, you then see it gives me the first four characters. So this is for extracting or pulling out a substring. Negative numbers will count backwards. So if I run that, it now gives me the last three characters of apple, the last three characters of banana, and the last three characters of pear. Cool. So that's the basics of string R. There's obviously a lot more, and you'll have to play around with it and get your head around it. But that's the simple version there of string R. Now, let's talk about matching and regular expressions. This is one of the most, when you're working with text data, this is one of the most basic or common sort of types of string manipulation that you'll want to do. If most of your data analysis revolves around numbers, so perhaps survey data or things like that, then you won't necessarily work as much with strings. But if you're working with text data, so tweets, documents, various things like that, then this is what you'll do quite often, is you'll, anytime you do any sort of natural language processing or text analysis, you're going to encounter messy data. You're going to encounter paragraphs that are full of things that you don't actually care about, or full of sort of junk pieces of data, or things that you don't actually need in your data set. And we can use regular expressions to match strings and remove characters, or remove emojis, or remove all blank space, or remove all words that we're not interested in our analysis. We can clean them out of the actual text. So we'll talk a lot more about specific text analysis techniques in a later session. But for now, let's look at some of the basics here. So regular expressions at the highest level allow us to describe patterns in our text. And then we can look for those patterns within a larger corpus, a larger body of text. They take a little while to get your head around and a little while to understand, but then you'll find them extremely useful. I'm only going to cover some very simple regular expressions in this session because, believe me, they can become complete nightmares if you look at some very complicated ones. So it's worth starting slowly and use them as you need to. So in this session, to learn regular expressions, I'm going to be using string view and string view all. All that these functions do, as you can see there, is they take a character vector, so that's a string, and they take a regular expression and they show you how they match. So I'm going to start with a very simple regular expressions, and then I'm going to build up to a bit more complicated as we go from there. So let's jump into with a simple basic match. So I've got my same vector here with three strings, apple, pear, and banana. and then I want to match Anne in that. So we'll start very simple, and then we'll build up from there. So let's run this, and we see that this regular expression Anne appears not at all in apple. It appears there in banana just the first time because we haven't told it to match it more than once, and it doesn't appear there in pear. So that's the basic idea with regular expressions, is to look for substrings within strings. Now you can imagine that instead of banana, if this was an entire book and I was looking for every occurrence of Anne in that book to remove it or to delete it or extract it or count it or something like that, then this would be very useful. All right, so that was the simple sort of basic match. Now let's look at something a little bit more complex. We want to match any character except a nude line. So let's run this and see what we find from our same strings there. So now I'm looking for A, and then I'm looking for a character either side. So the full stop, the point, looks for any character. But the pattern I've given it, I've said, is look for any character, and then an A, and then any other character. And this appears like that. If I were to delete the second full stop after the A and rerun this regular expression, I'm just going to get any character and then an A. I don't get the character afterwards. So let me run this again, and you'll see there that I've told it I'm looking for three things: some character, then an A, and then another character. So find that pattern within these strings. So it looks through, and that's what it finds. So if a full stop matches any character, as I said, that's what it does. How do we match an actual full stop in our string? If I had a string, a sentence, how do I find that? So for that, we need to escape it. As I said earlier, we use slashes to escape the actual strings that we're looking for there, the backslash, to escape these special characters. So let's run this here. So dot, I'm going to write this out as a line, and then let's see how we can find this with this line there. So there, by having the slash, the backslash before the dot, it's actually then looking for that there at that point. If I didn't have the backslash, it wouldn't find it. So that's the idea there. All right, so by default, regular expressions will match any part of a string. So they start at the beginning and they move through until they find, in this case, the first time that particular pattern occurred in the text, and then they move on like that. But it's often useful to anchor the expression to a particular part of the text. So to the start of the string or to the end of the string or whatever it might be. So you use the up arrow to anchor it to the start of the string, and you use the dollar to anchor it to the end of the string. So let's look at an example of that and see how that works. All right, so in the first example, we used the up arrow, and I said that's the beginning of the string. So what this is going to do is it's going to look for an A at the beginning of the string. In the second example, I used a dollar sign. So that's now looking for an A at the end of the string. And if I look at my three strings here, apple, there is no A at the end. Banana, there is, so it's found it. And pear, there isn't, so it hasn't found anything there. And then you can imagine that to force a regular expression to only match a complete string, we can say anchor at the beginning and anchor at the end. So in this example here, if I run this, I have apple pie, apple, and apple cake as my three strings. Now in the first string view, I've said match apple, and it matches all three of them because it doesn't have anything else to do. In the second one, I've said start at the beginning, look for the characters apple, and then stop at the end. Well, the only case where that's matched is this one. So we can build them up like that. Great, so I'm just going to go quickly through this here, but we can also use to look for various character classes in our strings. So there are a number of sort of special patterns we can give. So \d will look for any digit, so that's any number. \s will look for white space. So a white space is spaces between words or tabs or new lines. ABC, in this case, will match any of A, B, or C. So if I were to add D, E, F, that's going to look for any of A, B, C, D, E, and F. So basically we can create a subset, and we can say if any of these characters, find them, and then extract them. And then in this case here, by putting within square brackets and an up arrow, it matches anything except A, B, or C. So I think this is fairly abstract, and the idea of this session is just to get your head around the basics of this. We'll talk a lot more about actually how and when would we want to even use this in analysis in a coming session. So the next step, or the next level up, is to be able to repeat things. Remember in some of these examples, so in this earlier example here, I was looking for A, and it only found it once, or AN, it only found it once, but that appeared twice in the string. So we need to be able to say, look for this pattern or this occurrence more than once. So what we can do is we can, question mark is 0 or 1, plus is 1 or more, and then star is 0 or more. So let's run this and see what we get. So in the first one here, I said question mark, and question mark is 0 or more, and we're looking for the character pattern CC. So we've only found CC once there, 0 or 1. We can see that CC appears once there, but also once there. We don't find the second one because it only looks for the first occurrence of it. If we look at the second one, I've said look for CC, but you can find it twice, one or more times. So we find the first instance, and then we find the second instance there. And then in the third string, I said look for this pattern, LX, and look for it plus, so one or more times. So we can see that C, LX, we find that, and then the X can be repeated as part of that there in that match that we've looked for. We can get a little bit more specific. We can actually specify the number of matches precisely. So if it's within a squiggly brace, we can say match it exactly n times. So in this example there, I said find C exactly twice. We can say n or more if we have n comma. So here I've said find a C 2 times, 2 or more times. And then here at most m, and then between n and m. So in this case I'm saying find the character C between 2 and 3 times. So we can get very specific about matching these different patterns. As I said, just to remind you why this is useful, the idea of this is when you pull in a massive amount of text. So I've done some analysis where I've extracted ads online, for instance, for jobs. There's a lot of random text that you don't care about, and you need to throw out non-useful words or white space or punctuation marks or all things like that. So you end up crafting these regular expressions to throw out the junk. So you're only left with the actual text that you want to do your analysis on before you can then go and do some sentiment analysis or whatever the case might actually be. All right, so now those are the very basics of regular expressions. Let's think about how we can actually apply them to do some real-world problems. So just a quick word of caution before we continue. Because regular expressions are so powerful, it's often easy to try and solve every single problem with a single massive regular expression. Now I fell into this trap many times myself, where you try create this multi-line beast of a regular expression to try find some very specific match of text. What you mustn't forget though is R is a programming language, and you can use other tools at your disposal. So other functions, other loops, other things like that to find what you're doing. So it's often easier to write smaller, more specific, simple regular expressions rather than writing very large, very complex regular expressions. So rather break it up into multiple small ones than one big, very complicated, messy regular expressions. I've seen some programs come up with regular expressions that are hundreds of lines long. Believe me, it's not useful. No one can understand that. It's not a good way of doing it. All right, so R gives us some tools that actually help us make this a bit easier. So we can use detect to detect matches in our strings. So to determine if a character vector matches a pattern, we can use string detect. Remember, this is all from the string R package, so str_detect, and I can say look for E in this pattern. So Here we go, and it says true, false, true. So what's that telling us? Well, it says that in the first string, E is there. In the second string, in the word banana, there is no E. In the third string, there is an E. So it's telling me, is E in this string? Now let's run the second one and see what we get here. So what am I doing with the second one? Is I'm looking for a subset of the words here in this data frame, and I want to find out from this words, which is built into stringr. I want to find out which words have X in it. So now it's giving me all the words that have X in it, and I'm using string subset, which basically is I'm extracting those and I'm creating a new version of those. Okay, now let's run this and see what we get here. So what am I doing? I'm counting how many times a word appears in a given table. So I've shown that the word box or tax or six or whatever it is appears this many times in the paragraph, in the words paragraph. Now that's fine, but we can actually do that a bit more efficiently here because we've got string count. So we can do that with string r. So in this case, the word A appears once in apple, 3 times in banana, and once in pear. So much more efficiently, we can count how many times something appears there. And we can combine these together because, for instance, I can say that I'm looking for these vowels, so A, E, I, O, U, and I'm looking for that within the words data set. If I run words, you can see it's a massive data set of hundreds of thousands of words. I want to know how many times do these vowels appear, and then I want to take the mean of that. So there we can see that, sorry, let me run this whole line, that on average there's 2 vowels per word. Mildly useful, but those are things we can do there with these regular expressions. All right, so we can extract exact matches. So I've shown you the words data set. stringr comes with a sentences data set with 720 sentences. It's from Harvard, and we can then just see, here's an example of these sentences. This is the first 6 sentences there. The birch canoe slid on the smooth planks. Rice is often served in round bowls. So these are used to test out voice over Internet Protocol systems, but we can also use them to practice some regular expressions on them. So in these 720 sentences, I want to see, for instance, how many times or which sentences have these words in them. So I've got colors, red, orange, yellow, green, blue, and purple. And I can say, look, take this combination here, collapse it, and then look for that match. So if we run that there, that's what I want to match. And let's find which sentences have these words in them. So for whatever reason, I want to know which sentences have these in them. All right, so those are the sentences that appear. So I can tell you in these 720 sentences, we only have in the first 6 blue and red, but we don't know which sentences are actually in them. So we'd have to look a bit further at that there. But for this, we're using string extract. And we're saying string subset. So remember I showed you up here, we have subsets. Let me find it here. And this gives us, it extracts a subset from the original string. So we're looking for those colors. Where am I here? From the sentences, extract those color options there. So what I'm doing with this, we call that a pipe. Don't confuse it with the actual pipe in R. It's a vertical bar. That's just combining them together, and that stands for OR. So what is this saying? It's saying red or orange or yellow or green or blue or purple. So look for that within the string. Okay, so other than looking for subsets, we can also do matching, replacing. So string replace and string replace all will do exactly what you'd expect. They'll look for a match, and instead of just telling you that it's there, they'll actually replace it. So let me run this and you'll see. Sorry, let me run it. So in the first example here, I said string replace any vowel, so anything in that pattern, so A, E, I, O, U, any of those letters, replace it with a dash. And in the second one, I said replace all within X there. So with this first one, it's only going to be doing it once, but replace all is doing for all of them. So what's the difference? Well, in this case here, replace, it looks for the first example of a vowel. So in this case, A, E, I, O, U, and it's matching it with a dash. With replace all, it looks not only for the first one, but all the times that that pattern is matched and replaces it. So it's often important to think about when you're matching strings and things like that. Am I wanting to do just one, or am I wanting to do every single example in it? So in many cases, when I'm wanting to strip out white space or strip out irrelevant words, I might have identified a word, and I know that this appears in every single ad that I'm analyzing or in every single tweet that I'm analyzing, and I don't need it in my analysis. Then I want to replace all of it with, say, white space, or replace it all with a space character, and then I delete that, or whatever the case might be. We can also do string split. So I'm taking the sentences, and I can then, I say, let's take the first 5. So head gives us the first 5, and then I'm going to split them up. So what's that doing? We're splitting up each word into its own string instead of one long sentence. So that's also something we want to do. We'll talk about that a lot more when we do natural language processing and sentiment analysis with tidy text. Because in essence, with those models, we treat, it's called a bag of words. I don't want to go into it too much now, but the idea is to take a full book or multiple books or text or tweets or ads or speeches, and you analyze every single word on its own in relation to the other words, but also on its own. So we need to be able to split up all these books into individual words and then deal with the words on their own. But we'll talk about that when we get there. All right, so that's the basics of strings. Quick run through. I think it's something worth spending some time practicing and playing around with that. It's not necessarily straightforward from the get-go. All right, so now I'm going to talk about a second data type here. We're going to talk about factors. So in R, factors are what we use to work with categorical variables. So those are variables that have a fixed and known set of possible values. So for that, I'm going to use the 4cats package, which again is part of the core tidyverse, so you don't need to import it separately. So how do we create factors? Let's look at an example here with the months. So this variable has 2 problems. There are only 12 possible months, so we want them to be factors, not strings, because we can make typos, and we don't want to have that as the case. So jam is a typo instead of Jan, and we'll see how we can prevent that with a factor. The second thing is strings don't know what the order should be, so they don't sort in a way that makes any sense. So if I sort this, we have April, December, January, March, so it's just done it alphabetically. But that doesn't work for the months. We want to be able to actually sort them in a way that makes sense. So whatever category you might have in your data, we can create it as a factor. So how do we fix this? So we can fix both of these problems with a factor. And in this case, to create a factor, we need to specify what are the valid levels of that factor and what order do they come in. So in this case, I've said January, February, March, all the way through to December, and that's the order. So I've created this month levels variable, and now what I can do is I can say, take x1, these are the levels, and turn it into a factor. So factor x1, and then do it like that. So let's see what that looks like. So it's given us the same thing, December, April, January, March, but now if we sort it, it knows that the order needs to correspond to the levels that I've given it. So now that's some common sense there on the actual the factor. And you'll see when you do lots of different types of analyses, so regressions, various things like that, if you're adding categorical moderators or whatever the case might be, you need to have your variables in the right data type, so factors or strings or whatever the case might be there. This is especially useful for visualization, which we'll spend a lot of time on in the coming sessions, but factors are very important for visualizations. All right, so for the rest of this session, to look at some other things to do with factors, I'm going to be using the General Social Survey. It again comes built into the 4cats package. It's a long-running US survey on various social questions. So we can see here that it's got some details on marital status, the party that people support, political party, their religion and denomination, and the number of hours they watch TV, and income and race and age, and various things like that. So it's a general survey on a bunch of different things. So here's the data, and look at the different category options and counts, for instance, for the marital status variable. We're going to spend a lot more time plotting this and things like that. So let's see. So same data set. I'm now looking at the marital status, and I'm plotting it. Don't worry too much about the details of ggplots. I'm going to spend at least one session, if not two, going through ggplots and all the various details of what we're actually doing here. But for now, we've created a bar plot of the counts for the different marital status variables. When working with factors, the two main things we'll want to do is change the order of the factors and change the values of the levels. So in this case, we have marital status going from no answer to married. It's not quite clear what the order is, or does the order even make sense. So let's look at how we can go about using forcats to change the order of these factors into something that makes a bit more sense in our analysis. So for example, say I want to explore the average number of hours that someone spends watching TV per day across different religions, for instance. So if I plot this, it's difficult to interpret what's going on in this plot. We've got the various religions that the data set has, and we have hours of TV here. It's impossible to make out any patterns in this data set in the way that it currently is. So let's see how we can go about reordering it. So reorder takes in the factor whose levels you want to modify, a numeric vector, which is we can use that to actually reorder the levels, and then we can run function if we want to do more complicated things. But let's look at a simple example here. So what do I want to do? I want to reorder, so I use FCT because it's the forcats package, and I say FCT reorder, and the first thing is I say I want to reorder the religion column. So that's the first variable you give, and the second variable you give is by what do you want to reorder it. So if I were to just give it on its own, it would do descending or ascending. But here I say I want to reorder the religion column by the TV hours variable. So let's plot this again and see what we actually get. So now this can tell us something a bit more interesting. So it makes it easier to understand that people in the don't know column category watch much more TV than, say, for instance, Hinduism or other Eastern religions or whatever the case might be. So oftentimes reordering your data, if there's something that you actually, if there's an order that makes sense, can tell us a lot more about what's going on. So as you sometimes make more complicated transformations in your data, I'd recommend moving this reorder step here outside of the plotting step. So here we did it in the plot, and again I'll come back and talk about plots in a lot more detail in a coming session. But I would recommend having that happen before you get to plotting. So use it in a mutate. So let's run this again, and you'll see it'll do the same thing. But what I'm doing is I'm saying, take the religion summary dataset and then pass it to the mutate function, create a new variable, we can call it relig, where I'm using reorder, and I'm saying take the relig column and reorder it based on TV hours, and then give it to the plotting function. And again, we'll talk about the details there and put a plot like that. Great. So let's look at another example of this and see what we can do there. So in this figure, we are wanting to plot age versus income. Now here, this is a bit different. So what if we want to create a similar plot here, but we don't want, this is to illustrate how reordering is not necessarily always a good idea. So with this example here, there's no natural order to the various religions, whereas here, age has an order to it, as well as these income categories. So it doesn't necessarily make sense to always reorder. So you must only reorder when the levels are originally arbitrary. But if there's a natural order, so income is ascending and age is ascending, then it doesn't make sense to reorder. So this is the marital status there. In this case, you can reorder it because there's no order to never married versus divorced. But it makes sense to, in this case, order it based on increasing frequency. So what we can do is we can take our data set, GSS cat, and we can pass it to mutate, and I can say, let's create a new variable marital. So take marital and then reorder it based on infrequency and then reverse that. So what am I doing? I'm saying FCT infrequent. So the more frequent it is, the lower it will be, but I can then reverse that ordering and then we can plot that. So that makes sense. There's no problem with that plot because there's no natural order. So that's fine. All right, so that's the first thing we want to do with factors. We want to change the order. The second thing you might want to do with factors is modify the factor levels. So this is often more powerful or more interesting. So let's look at an example of that here. So I've got party IDs. These are political party IDs, and there are a number of ones which aren't necessarily that useful. So I might want to clarify the labels a bit. So if you look at this example here, they're inconsistent, no answer, don't know, other party, independent, near Republican. We're not quite sure what's going on here. So let's tweak them, make them a little bit longer, and make them a little bit more useful. So for that, we can use factor recode. So again, we take our data sets, and you'll see this pattern again and again throughout these sessions. And we pass it to mutate, and then we create a party ID variable, and we say party ID is going to be equal to factor recode. And then what we do is we say, if it was equal to this, it's now going to be that. If it was equal to, this, we're going to give it that value. If it was equal to this, it's going to be that. So we're changing, the right is what it currently is, and the left is what we want it to be. So we're reordering like that as we go through the data sets. So here we're saying strong Democrat is Democrat, comma, strong, and then not STR, Democrat with a small d, Democrat, comma, weak. So we can reorganize the different levels of our things, and we can count them up like that. So let's see. We have the same data, that hasn't changed, but we've organized the levels differently. We've made them more consistent. So that's factor recode with the 4cats package. Now, what we also want to do sometimes is combine different levels, and we can obviously do that here because we can say, for instance, that no answer is equal to other, don't know is equal to other, and other party is equal to other. So you don't only have to assign them one-to-one, you can assign multiple different ones to a variable. So now if we run the count on this, we'll see that other is a lot more than it was in these data sets because we've combined 3 levels into one. Great, so the last data type I want to talk about in this session, the last 5 minutes here, is dates and times. I'm only going to scratch the surface on dates and times just because I think you need to know something about them, but they're not something that you necessarily work with all the time if your data sets don't involve dates and times and things like that. You'll use them from time to time, but not all the time. So in almost all programming languages, dates and times are problematic. They cause a lot of confusion. They're often very complicated, not so easy. So think about these 3 questions I have here on the screen. Does every year have 365 days? Well, the answer is actually no. Does every day have 24 hours? No. Does every minute have 60 seconds? No. So there's a leap year. So not every day has 365 days. In many parts of the world, there is daylight savings. So you often get some days that have 23 hours when the changeover happens, and other days that have 25 hours. We also have leap seconds. So not every minute is 61 seconds. So it gets very confusing with dates and times. The idea is, or if you want to know why it's confusing, basically dates have to reconcile physical phenomena, so the rotation of the Earth and its orbit around the Sun and the irregularities there, with geopolitical phenomena, months, time zones, daylight savings times, political things like that. So I'm not going to go into a lot of detail at all on lots of those different things, but it is worth understanding that there's some tools out there for dates and how you can actually work with them. So for that, we're going to focus on the Lubridate package. This is again part of the tidyverse, so it works in that same structure, but it's not a core tidyverse package. So you need to load that into your environment when you want to work with it, because dates are not something that you work with that often, so they haven't included it in the core tidyverse. I'm also going to be working with the New York City flights dataset. This is just a dataset of flights coming in and out of New York. Okay, so how do we create dates in R? There are three types of dates that we want to refer to normally. We've got a date, so that's the date. We've got time within a day, and then we have date time. So that is a date plus time. So that is the day, the given date of the month, as well as then the actual time. So I'm going to focus on these ones in this session. So let's see. If we want to find out the current time, we can type in today. That'll tell us the current date. Sorry. So in this case, I'm running this on the 16th of May, 2020, and that gives us the date right now. If I want to find out the current time, I can run now, and that will give me the date as well as the time. So I'm running this at 5:29 and 46 seconds South African Central Time on the 16th of May, 2020. So that's the first thing there. That gives us the current date and time and things like that. How do we work with dates in other formats? So say you collected some data and it's stored in a CSV and you have a column for dates. They're not going to be saved as dates in your, they're going to be saved as strings. So that you might receive different things like that. And Lubridate, this function, this package here, has hundreds of different packages and functions to be able to clean up different types of date formats and put them in something that R can actually understand. Hey, this is a date, this is not a string. So say you received any one of these three, you can then work with that. So we can say, in this case, this is year, month, day, because it's got the year, then the month, then the day. In this second case here, it's month, day, year, and Lubridate can work that and understand what the ST means and things like that. And this one, it's day, month, year. So it can understand hundreds of different formats and turn these into actual correct date formats or functions. So the idea with dates is also with strings, if you sort them, it doesn't sort them in a logical order because it doesn't know necessarily that the 28th of February is after the 31st of January. It'll just do them by number. Whereas a date, it can actually sort that and we can perform calculations and things like that. So the same idea here, we can write in a whole bunch of numbers and we can say these numbers actually correspond to a day. Let's work with that there. Same thing here with dates, hours, and minutes. We can run with them like that. So if you ever are doing an analysis that involves time series and things like that, you need to first create date objects, and then if you want to plot them or whatever the case is, R knows how it can actually work with the data like that. So let's see how we can do that here with this flights data. So flights has some columns, month, day, hour, minutes, and so on, but this is not in any kind of format that R knows corresponds to day, month, year, things like that. So we need to mutate these. So for that, we've selected the columns we want, so that's these columns, and then we're going to mutate, and we're going to give it a departure time, so that's the date and the time that it departed, and for that we can use the make date time function. So for that we say, here's year, here's month, here's day, here's hour, and here's minute, put them together and store them as a date time. So if you can look here, the data types in this case is integers and doubles, so that's for numbers basically, but here that is a date time data type. And now it knows the order of those. We can perform calculations and things like that with various dates and stuff. So let's visualize that and see what that actually looks like. I think I've got a visual coming up for that. So now I've done that here for departure time, scheduled time, arrival time, and scheduled arrival time. So I've just done that for all the various columns in the data set. So that's just what I'm doing there. And we can visualize that here. So this is a histogram of, in this case, departure time and the counts for the various departure times. it knows the order of these. So it knows, for instance, that July 2013 or January 2013 is earlier than January 2014. If it wasn't a date time, it wouldn't know that the two Januaries are different. It would just put them together as January. So it's very important for any kind of time series modeling and things like that you're doing, that you work with the proper variable types for date time. We can do the same thing here. This is within a day. Again, I'm not going to talk about the actual plotting for now. We'll get to that in a later session. But this is then departure times and counts of flights over the course of a day. And it needs to know that 12 noon is different to 12 midnight for the data to actually make sense. We can look at the different components, so we can extract out year from a date time. So here we've got year, month, day, hour, minutes, and seconds, and we can say what's the year, and we can say what's the month or what's the day, and we can extract anything from that there. We can also extract Y day. So what is Y day? That is year day. So that is what day of the year is the 8th of July 2016? Well, in this case, it was the 190th day. So there is an order to it that it can work out. And weekday is what day of the week was that? So I don't know off the top of my head, but that says that the 8th of July 2016 was the 6th day of the week. 6th day of the week corresponds to, in this setup, that's a Saturday. And it can tell us what the actual month is. So I've given it this variable, and I say, what is the month? And label it as true. Well, label basically means July instead of 7. So we can label it. And same thing here for weekday. So weekday will just give us the number of the week, but I can actually say, tell me what day of the week that is. So in this case, it is Friday. And these are the different options for it there. Great. So we can use those for looking at different patterns in our data sets. So let me just get to what I actually want to do with this last bit is looking at durations and periods. So say we want to know, for instance, how old is South Africa? So where I'm recording, it's on the 16th of May. We can work out and do calculations with dates. I can say, what's the difference between today and the 27th of April, 1994, Freedom Day here in South Africa. And I can tell you that South Africa's age is 9,516 days old. So that's how many days have passed since Freedom Day. Quite nice. So we can work out durations with our date times. So this says that's roughly, if I say, I don't care about the specific days, I want to know the duration. It's roughly 26.05 years. So almost 26 years. We can do calculations. So I can say, what is the number of years multiplied by 2, or whatever the case is. So we can do different calculations and things like that. But oftentimes, these durations are not super intuitive to understand and not super interesting on their own. We want to look at periods because, well, as humans, that's how we think. We think in periods. So if I say 6 months plus 1 day and 10 times that, what is that? Well, that is 60 months, 10 days, and no hours, no minutes, and no seconds. We work in that kind of language here. If I run this line, I say 50 days plus 25 hours plus 2 minutes. It then creates that there, and you can use that in a calculation if you want to there. I went through dates really fast. It's something you need to spend a bit more time going over yourself. Factors, strings, dates, all these basic data types underlie all the various analyses that you might want to do. And they're not something that you should just skip over. If you run a regression analysis and you don't have the variables as factors, you've left them as strings, your moderation or your various categorical interactions that you're looking for won't work out. You'll get some result, but it'll be bogus. It'll be junk. So the data types are very important. With these dates, if you're doing all the modeling that's going on at the moment with coronavirus and things like that, all relies on time series data. So you need to make sure that you've actually got your data types as date times, so you can actually do that correctly. So it's very important to think about the data that I'm working with. Is it a string? Is it a factor? Are they levels? Are they categories? Is it a date time? Is it a number? Whatever it might be. And that tells you what it should be. And luckily for us with the tidyverse, there's nice functions for every single different data type. So we can do different things with it. And our life becomes a lot easier as we go through if it's the right data type. So for that, just as a reminder, this is from chapter 14, 15, 16, and 20 from R for Data Science, and the links to the chapters there are there. Great, thanks for listening. I'll see you in the next session.